Again, welcome to DSRT 734 class, Inferential Statistics in Decision Making. These lectures cover multiplication rules for probability. So our main objective again is to go through multiplication rules for probability and conditional probability. And we shall see some few examples also solving the problem. So we start with the definition of conditional probability. Here we say the probability that an event will occur given that some other event has already occurred or is certain to occur is a conditional probability. So for example, the probability that a person will get a lung cancer given that he smokes cigarettes. So this is the definition and also the formula to find a conditional probabilities. So our notation here read as probability of A given B. So the vertical line, we are going to represent it as given. So probability of A given B, which means what is the probability of getting A if B already occurred? It's equal to probability of intercept A and B. Again, A and B intercept means both events occur at the same time. Event A and B occurred at the same time, divided by probability of B. So again, probability of A given B is equal to probability of A intercept B divided by probability of B. Now, probability of B given A is equal to also probability of A intercept B divided by probability of A. So if it's B given A, we are going to divide by probability of A. So let's see an example. Here we say, suppose a marketing research firm has surveyed a panel of consumers to test a new product and produce the following cross tabulation, indicating the number of panelists that like the product, also the number that did not like the product, and also the number that were undecided. And this is our table. So this is a market research survey. We have the age between 18 to 34, 35 to 50, and over 50. And we can see the number of surveys that like, and also not like, and undecided. This is the total. So the total of this sample is 1,403 people. Now, our question is, if an individual is between the age of 35 and 50 years old, what is the probability that he or she will like the product? So this is a conditional probability. The condition is the age. What is the probability that I will like the product given that my age is between 35 and 50? So we need to go to the table. And here we say, let the event A represent like the product, B will be the age between 35 to 50. So here we are going to look probability of A given B. So that will be the probability of A intercept B divided by probability of B. So first we can look for probability of A intercept B first, which in our previous lectures, we went through the concept, how we find A intercept B. And this is the formula here. Probability of A intercept B means we are going to look for the number of persons that like the product. Remember, event A means we like the product. B is between the age of, I think, 35 to 50. So when we go to the table, we are going to look at how many people like the product and their age is between 35 to 50. So that is probability of A intercept B. Both of them occur. It's 193, but we can go back to the table and see. So we can see the table here between the age of 35 to 50 and they like the product is 193. So probability of A intercept B will be 193 divided by 1,403. Then we need to look for probability of B. Now, probability of B, remember B is the age, and the age is between 35 to 50. the total people in that age group is 444. So probability of B will give us 444 divided by 1403. Then we are going to divide again probability of A intersect B divided by probability of B. Again, one more time. The question said we should find the probability of being between this age, 35 to 50, and I would like the product. So let's assume again, like means A event. The age group means B event. So we are looking for probability of A given B, which first to equal to probability of A intersect B. How do we find A intersect B? We go to the age group and the like is 193 because event A is like, event B is 35 to 50. So we get that value 193 divided by the total value. So that will give us A intersect B. Then what is the probability of B? B is the age, the total age group in the sample is 444. So we divide 444 by 1403. Then the final solution, probability of A given B, will be the two values that we find. That is probability of A intersect B divided by probability of B. So let's continue with the solution. So this is again the probability of A intersect B, 193 over 1403, and that gives us 0.1376. And as we said, the probability of B will be the total people in that age group. Is 444 divided by the total sample. Then the probability of A given B is 0.1376. That is the probability of A intersect B divided by 0.3165, which is probability of B. So our final answer will be 0.4348. So we can say that this answer could have also been obtained by simply dividing 193 by 144. But again, we want to show the step by step because probability of A given B, when you look at the table, we can go straight forward and say, okay, probability of A given B, the intercept, how many people fall in that group of event A is 193. How many people fall in the event B is 444. So we can just divide 193 by 444. And that also will give us 0.4348. And most textbook, again, that's how we find the probability of A given B. We don't follow this kind of two steps. We don't need to find individual probability of B and probability of A intersect B and divide it two. Again, you get the same as solution. Now, let's see a second example here. Here they say out of 300 applicants for a job, 212 are male. Of the male applicants, 110 have served in the military. Now, what is the probability that a random chosen applicant has served in the military, given that it's a male? So we can say this is a conditional probability. Probability of serving the military, given that you're a male. So first thing we have to look at, how many people were in the military? That's a male that served the military. That is probability of A intersect B. Let's say A is the military, serving the military, and B is male. Then we will say, here they say 110 have served in the military of the male job. So it will be 110. And how many is the total male? It's 212. So again, we can divide 110 by 212, or we can go through the two process by first of all, find the probability of A intersect B, which will be 110 divided by 300 because that's the total applicants. Then probability of B will be 212 divided by 300. Then we divide the two values. Now the second question said, if 152 of the applicants have served in the military, what is the probability that a random chosen applicant is a male, given that the applicant has served in the military? So let's see the first solution. As we said earlier in the first solution, we can see right here, again, it's up to us. First thing we look for, the probability of A intercept B, which will be 110 over 300, because 110 people, they have served in the military and also they are male. So it's A intercept B divided by the total sample. Then the total male is 212 from the sample. So that will be our probability of B. So 212 divided by 300. Then this will calculate our first solution. Or as we said, we can just divide 110 by 212. That will give us the same answer. So again, actually, when we write this, we can see the 300 will cancel the other 300. So final answer will be 110 over 212. So probability of male and military service, A intercept B, or male intercept military service. It will be 110 over 300 because we have 110 male that have served the military and the total population sample is 300. Probability of male, we have total of 212, so divided by 300. So that's what we said. We can just divide the 110 by 212, and that will give us 0.5189. Now let's go to the second question. For this question, we want to calculate the probability of male giving military service. So you can, now from this solution, we will see that probability of A giving B is different from probability of B giving A. So here we know from part one that the first solution that the probability of choosing one of the 300 applicants who is a male and has served in the military was 110 over 300. Also, we know that probability that randomly choosing applicants has served in the military is 152 over 300. Now, using this conditional formula, we can solve the problem. So this time it will be probability of male giving military service divided by probability of male and military service. So the previous will be okay. 110 over 300 is fine because A intercept B. Probability of A giving B is equal to probability of A intercept B divided by probability of B. Now, probability of B giving A is also equal to probability of A intercept B, but this time divided by probability of A. So here we can see that next it will be 152 over 300 because the randomly selected 152. So using the formula, this is what we get: 110 over 300, 152 over 300, and that gives us 0.7237. So here we noted that we can see that probability of A giving B is not the same as probability of B giving A. Previously, we find the probability of serving the military service given that you are male. Now we are looking for probability that you are male given that you serve in the military. Now, another example here, they say we should conduct the experiment of rolling a fair die 2 times. Consider the 2 events. A will be rolling a 6 on the first row of a fair die, and B, rolling a 4 on the second row of a fair die. Are these 2 events independent? Yes, they are independent. Why? Because previously, for example, conditional probability, the 2 events, event A and B, they are not independent because B can determine A based on some probability value. So probability of A giving B means that 2A and B are not independent. But rolling a die, if I toss a die the first time, if I get a 6, that doesn't mean I have 50% chance or 100% chance of rolling 4 or rolling any number. So the numbers can be random. So these 2 events are independent. So here we say, since the knowledge of the outcome of the first row does not help one make an inference about the outcome of the second row, the 2 events are independent. Now, smoking cigarette, getting a lung cancer, we can say the 2 events are dependent because there's a study that if you smoke cigarette too much, you will get a lung cancer. There's some percentage of chance that you get a lung cancer. So that will lead us to independent. How do we find probability of A given B if A and B are independent? Now, probability of A given B is equal to probability of A, and also probability of B given A is equal to probability of B if the A and B are independent. And this is the definition here. So if we have two events, A and B, and they are independent, then the probability of A intersect B will be probability of A times probability of B. Now, if we have more than two events, then we just multiply all the probability of each event. So let's see an example here. A coin is flip and a fair die is roll. Find the probability of getting a head on the coin and also an even number on a die. We can use the tree diagram to find the probability, or we can use the probability law 10 to find, which is, in this case, the events are independent. The events are independent. So we know probability of A and given B, if if we have two events A and B and they are independent, the probability that both will occur, which is probability of A intersect B, will be probability of A times probability of B. So the solution here, we are using the tree diagram. So how many possible tossing and then a coin or dice will be? Now we know a coin have only head and tail. A die may have 6 sides. So 1, 2, 3, 4, 5, 6 sides. So here we have the tree diagram for flipping a coin and rolling a fair die is given. Note that there are 12 equally likely outcomes because the coin have two sides, head and tail, and the die have 6 sides, head, 6 sides, tail, 6 sides. So we can see H1, H2. Now I toss the die once. I roll a die once and I toss a coin. The coin is H. I may get possible 6 here. T also possible 6. Now our question said, what is the probability of getting either head or tail and also getting even? So even will be 1, 2, 3, head, 1, 2, 3. Now if it's a tail and it's odd, then we have T1, T3, T5. So we can, the total 9 is 12. So we can say 3 by 12. Now let's look at the solution. The tree diagram for flipping a coin and also rolling a fair die is given. Note that there are 12 equally likely outcomes because I can get head and also 1, 2, 3, 4, 5, 6 side. I can get tail and I can get up to 1, 2, 3, 4, 5, 6 side on the die. So we have 3 outcomes in the red are those where the coin toss result in a head and the roll of a die result in even number. So it will be 2, 4, or 6. Now, when we look at our question here, they say the coin is flip and a fair die is roll. Find the probability of getting head and also an even number on there. So first we are using the tree diagram. So this is very straight. We have head and even number is only 3. So totally it will be 3 divided by 12. So 1/4. Now we can also use our probability law 10, which is independent event. If events are independent, what's the probability of finding the intercept of them? So here we are going to do multiplication. We say since the event of tossing a coin is independent of the event of rolling a fair die, we can use the probability law 10 and multiply the probabilities of each event together. So here, probability of head and even number, it will be half times 3/6. Why half? Because when I toss a coin, the chance of getting a coin have only two sides, head and tail. So the chance of getting either the head or the tail is half, 0.5. So probability of head is half. Now probability of even numbers, we have 3 even numbers out of 6. So that also is half, which is in this case 3/6. So the answer will be 1/4. So we can see that either we use the law 10 is the same as using the tree diagram also, the same solution. So a coin is flipped and a die is rolled and a card is drawn from a standard deck of 52 cards. Now we can see that all these three events are independent again. We flip a coin, we roll a die, and then we draw a standard deck of 52 cards. Now the question says, find the probability of getting a tail. That will be half. A 5 on the die, so that will be 1/6. And a jack of clubs from the deck of cards. Here we have to know how many clubs we have. I think it's 4 clubs. If it's 4 clubs, then it will be 4 divided by 52. Again, this is using the law 10. Find the probability of A intersect B intersect C. It will be probability of A times probability of B times probability of C. So let's see the solution. Now we say since there is 3 events, flipping a coin, rolling a die, and selecting a card, they are all independent. So we can use the product rule. So here, probability of getting a tail on the coin will be half. Probability of getting 5 on a die will be 1/6. Now, probability of getting a jack of clubs. Okay, here they say I thought the probability of getting a club card will be 4/52. So a jack of a clubs, we have only one jack club in a card. So it will be 1/52. So we multiply the 3 values together since we are looking for the intersection. We multiply. So we get half times 1/6 times 1/52. And that will give us 1/624. So the probability of getting tails on the coin, rolling a 5 and then selecting the jack of clubs is about 0.0016. Next example, they say we should choose 2 cards from a standard deck, replacing the first card and shuffle before choosing the second one. What is the probability of choosing a king and then a queen? Is these 2 events independent? If they are independent, then we use the product rule. So here we say, because the first card is replaced before the second card is drawn, the probability of a second event occurring is not affected by the outcome of the first event. So this is again independent. So the 2 events are independent. Therefore, we can calculate the probability of using the product rule as following. Probability of king and a queen is equal to probability of king times probability of queen. How many kings we have, how many queens we have, and what is the total cards? And that will give us the solution. We have 52 cards, we have 4 queens, and we also have 4 kings in the card. So the answer will be 16 divided by 2704, which will be 0.0059. Another example here, this is an actual case that set up quite a controversy. People versus Collins, 1968. So on June 18, 1964, at about 11:30 a.m., Mrs. Brooks was assaulted and robbed while walking through an alley in San Pedro area of Los Angeles. Now, Ms. Brooks described her assailant as a young woman with a brown ponytail. At about the same time, John Bass was watering his lawn and witnessed the assault. He described the assailant as a Caucasian woman with a dark brown hair. As she ran from the alley, she jumped into a yellow automobile driven by a black man with a mustache and a beard. Now, several days later, the police arrested 2 individuals based on the descriptions provided by the assailant and also the witness. The 2 suspects were eventually charged with the crime. During the trial, the prosecution called a professor of mathematics to testify. Now, the prosecutor set forth the following probabilities for the characteristics of the athletes. So here we have the characteristics, a yellow automobile, and this is based on the Los Angeles data. So 0.10, man with a mustache, 0.25, girl with ponytail, 0.10, girl with blondie hair, 0.33, black man with beard, 0.10, and interracial couple in a car, 0.001. How did the prosecution use this probability to argue its case? So this is the solution. If the events are assuming to be independent, then the product rule can be used to calculate the likelihood of observing their joint occurrence. So P, probability of yellow automobile, and the intercept man with a mustache, intercept girl with ponytail, intercept girl with blondie hair, intercept black man with beard, intercept anti-racial. So here we are trying to find the probability of all the characteristics. And here the answer will be 0.10 based on the table, 0.10, 0.25, up to 0.00. So we multiply everything and the answer is almost 0, 0.0000825. Now, based on the product rule, the mathematician testified that there was about 1 in 12 million chance that a couple selected at random will possess these characteristics. Because again, different witnesses give different characteristics. Now, based on the population in that area, or I would say Los Angeles, we came up with the probability of each characteristics. So the prosecution added that the probability was the chance that any other couple possessed the distinctive characteristics of the defendants. So the jury convicted the defendants. On the appeal, the Supreme Court of California reversed the decision based on 2 main points. First, there was no proof offered that the probability used in the probability calculations were correct, and also there was no evidence that the events were independent. Second, the prosecution evidence pertaining to a randomly selected couple was not pertinent to the problem of the existence of any other couple possessing the same characteristics. So again, in a production process, a product is assembled by using 4 different independent parts. We have A, B, C, and D parts. In order for the product to operate properly, each part must be free of defects. Now, the probability of the parts being non-defective is given by following. Probability of A part is 0.9, B is 0.7, C is 0.8, D is 0.9. Now, our question is, what is the probability that all 4 parts are defective? So looking at this, first of all, they give us the hint here already. Using 4 different independent parts. So A, B, C, D are independent parts. So to find what's the probability that all the 4 parts are defective, we need to find the probability that A is defective, B, C, D, and then multiply all of them. But here they give us the probability of the part being non-defective. So if the probability of part A being non-defective is 0.9, then the probability of A, B defective will be 0.1. Probability of C part non-defective is 0.8. So B defective will be 0.2. So let's see their solution. So that's what we are saying here. Again, we went through A complement, B complement, C complement, the probability of a complement event. So A complement means 1 minus probability of A. So probability of B complement will be 1 minus probability of B. So as we said, probability of A was 0.9. So probability of A complement will be 1 minus 0.9 because 0.9 was the probability of non-defective. We are looking for the probability of defective. So it will be complement of non-defective, which will be defective. So our solution will be 1 minus 0.9, 1 minus 0.7, 1 minus 0.8, 1 minus 0.9 again. And the final solution will be 0.0006. So there's 0.06% chance that all the 4 parts may have defects. Now, the second part said the probability that the product does not work is the probability that at least one of the parts do not work, since each part must be free of defect for the product to work. So in this case, probability that the product does not work will be probability of at least one part does not work. And that will give us 1 minus P for all parts work. Probability of all the parts work. So this means we have to find 1 minus P, A intersect B intersect C intersect D. And this gives us 0.9 times 0.7 times 0.8 because the probability of A, B, C, D together is the probability that they are all working. So if we multiply everything and we subtract from 1, it will give us the probability that at least 1 is not working. And that gives us 0.5464. So another example says, what is the probability of drawing a king and then queen from a standard deck if the cards are drawn without replacement, which means that the first card is not replaced in the deck. Remember, we have the same example, but the card was replaced. This time we are not going to replace it. So the second probability means we are going to deduct 1 from the total amount of the card. So if the card is 52, probability of getting, let's say, club essay will be 1 over 52. Now, probability of getting king jack without replacing the essay, it will be 1 over 51 because now we have 1 card reduced. So let's see the solution here. This situation is essentially the same as the drawing 2 cards at the same time from the deck. But let's think of this experiment as having 2 stages for the async calculation. To make the calculation more easy, we start by first determining the probability of drawing a king from the deck. So since there are 4 kings in the deck of 52 cards, we get 4 over 52 or 1 over 13. Then the secondly, what is the probability of now drawing a queen? But since we are holding a king in our hand, there are still 4 queens left in the card, but we have 51 cards now. So which means our second probability will be, instead of 4 over 52, it will be 4 over 51. So here we can now find the probability of drawing a king and queen without replacement, again without replacement. And that will give us, again, 1 over 13 times 4 over 51. 1 over 13 is the same as saying 4 over 52. 4 divided by 52 times 4 divided by 51. Now, if with replacement, then it will be 4 divided by 52 times 4 divided by 52. So next, it will take us to the probability of law 3. Probability law 3. This is multiplication rule for dependent events. Now, previously it was independent event. Now, if 2 events, A and B, are independent, then probability of A intersect B will be probability of A times probability of B. Now, if 2 events are dependent, it's almost the same as conditional probability. So here we can see the formula. Probability of A intersect B is equal to probability of A times probability of B given A, or probability of B times probability of A given B. Now we can see from this formula is the same as the conditional formula. Now, probability of B given A is equal to probability of A intersect B divided by probability of A. Or the second formula we look here, probability of B given A will be probability of A intersect B divided by probability of A. So again, it's the same as conditional. We just changed formula transformation. Probability of B given A equal to probability of A intersect B divided by probability of A. If I'm looking for probability of A intersect B, then it will be probability of A times probability of B given A. So let's see an example. Assuming that there are 17 men and 24 women in a Lions Club, 2 members are chosen at random each year to serve on the hospitality committee. What is the probability of choosing 2 members at random, and the first being a man and the second being a woman? So we can see that this will be dependent concept. So the solution here said, note that since we are choosing 2 members, but these 2 members, when you look here, they say, what is the probability of choosing 2 members at random? The first being a man and the second must be a woman. Now, if it's independent, we can choose 2 men, we can choose 2 women, we can choose 1 man, 1 woman, it doesn't matter. But here we are looking for the probability that we are going to choose a man first, then the second should be a woman. So these 2 events are dependent, one depends on the other. So here we say note that since we are choosing 2 members, the first choice will influence the probability for the second choice. Because if the first choice is a woman, then the second choice have to be a man. If the first choice is a man, the second choice have to be a woman. So these 2 events are dependent. So this means that we are dealing with dependent events. What is the we want to find the probability of man and woman choosing A and B. Let's say A is choosing a man, B is choosing a woman. So we are looking for probability of A intersect B, which according to multiplication rule for probability law 11 is equal to probability of a man times probability of woman given man, or probability of a woman times probability of a man given woman. So when we first member is picked, there are 17 men out of 41 members. Now, when the second member is picked, we assume we have already picked a man so that the leaves all 24 women, but only 40 remain members. So our calculation will be probability of a man and a woman will be probability of a man. So if it's probability of a man, it will be 17 over 41. 17 over 41. Then since we already chosen a man, our total left is 40 now, and the women are 24. So it will be 24 over 40. And that will be 0.2488. Now we can go back to the question one more time and make sure we get it. So now, here we are assuming there are 17 men and 24 women in a Lions Club. 2 members are chosen at random each year to serve. What is the probability of choosing 2 members at random, and first being a man and second being a woman? So first 17, then our total members, and let's say here to be 41. So 17 over 41. Since they are again dependent, so we have to first of all look for probability of a man times probability of a woman giving a man. So that's what we have here. 17, the total is 41, so 17 over 41 times 24 over 40. Again, why 24 and why 17? As we said from the question, we have 17 men, 24 women. So the total will give us 41. So that means 41 together. So probability of choosing a man will be 70 over 41. But after we take the man out, we have only 40 left now. So times probability of having a woman giving a man will be 24 over 40. That gives us the answer here. So that will be the conclusion of these lectures. Again, these lectures will cover the concept of multiplication rules in probability, and that leads us to conditional probability. We saw some few examples and also the formulas. Thank you for your time and see you in the next lectures.